welcome Professor S.N. Singh as well as Professor Cipher Rugman to join this webinar. So first, I am extremely happy to introduce the first panelist, Professor S.N. Singh. Attained his M.Tech and PhD in Electrical Engineering from Indian Institute of Technology, Kanpur in 1989 and 1995. Presently, he is a professor HAG, Department of Electrical Engineering, Indian Institute of Technology, Kanpur, India. Before joining IIT Kanpur as associate professor, Dr. Singh worked with the UP State Electricity Board as assistant engineer from 1988 to 1996. With Roorkee University, now IIT Roorkee, as assistant professor from 1996 to 2000. And with Asian Institute of Technology, Bangkok, Thailand, as assistant professor from 2001 to 2002. He was Vice Chancellor of Madan Mohan Malviya University of Technology, Gorakhpur, during April 2017 to July 2020. Dr. Singh received several awards, including Young Engineer Award of Indian National Academy of Engineering, Kausala Research Award of IIT Roorkee, and Young Engineer Award of CBIB New Delhi. Professor Singh is a recipient of Humboldt Fellowship of Germany and Otto Manstead Fellowship of Denmark. Professor Singh became first Asian to receive 2013 IEEE Educational Activity Board Meritorious Achievement Award in Continuing Education. He is also recipient of INAE Outstanding Teacher Award 2016 and IEEE Region 10 Asia Pacific Outstanding Volunteer Award 2016. Dr. Singh is appointed as IEEE Distinguished Lecturer of Power and Energy Society from 2019 and Industry Application Society for 2019 to 2021. He is also recipient of NPSC 2020 Academic Excellent Award and 2021 IEEE Industry Application Society Outstanding Educator or Mentor Award. His research interest includes power system restructuring, facts, power system optimization and control, security analysis, wind power, etc. Professor Singh has published more than 500 papers in international or national journals or conferences and supervised 31 PhD, 12 are under progress. He has also written 23 book chapters, 6 edited books and 2 textbooks, one on electric power generation, transmission and distribution, and the second is Basic Electrical Engineering, published by PHI India. Professor Singh has completed 3 dozen of technical projects in India and abroad. His 2 NPTEL video lectures on HVDC transmission and power system operation and control are very popular. Professor Singh was chairman IEEE UP section for 2013 and 2014, IEEE R10 Asia Pacific Conference and Technical Seminar Coordinator 2015 to 18, and R10 Vice Chair Technical Activities. Presently, Professor Singh is immediate past chairman of IEEE India Council. Dr. Singh is fellow of IEEE USA, FIET UK, FNAE, FIE India, FIETE, AVH, and so on. So his credential goes on, and let me stop at this stage. And now, on behalf of Institution of Engineers and everyone assembled here, now I request Professor Singh to take over. Over to you, sir.
I'll share my slides. How to share? How I can share my slide?
Mr. Sudeep?
Yes, sir.
How I can share my slide?
You open it, sir. Your screen is visible. You open your PPT.
Okay. Okay. It is now.
Yeah.
You can see
Make
my
it full
PPT.
screen. Yeah.
Yes, sir.
Yeah. Make it full
Yeah.
screen.
Okay. Okay.
Yes. Yes.
Okay. Good afternoon to all of you. And as you know, the topic of this panel and other things. So since we are having time, so I'll quickly glance and I'll try to basically give the focus on the smart grid and other what are the changes happening in the electrical power engineering and why we are talking in the smart grid and still future we have to go and we are having the digital energy transformation. So quickly I'll go maybe the 10, 15, 20 minutes. Then other speaker will be speaking, Professor Cipher. He's, as you all know, he's also the IEEE President-elect candidate and the voting has started. So he will be talking and he's expert in the smart grid area. And then there'll be some questions and the panel, etc. So I thank Sudeep ji, Kumareshan ji, even though Institution of Engineers, the Rajamani, and even though other people, SDG and the Electrical Engineering Delivery Board Director. So all the people, those have involved in making this panel successful and that will be useful for our listeners. I can see at this moment we are having approximately 118 people, those have joined attendees, and many other will be recorded and that will be also showing the different social media as well. So I'll be going quickly and just to start with what is happening in our country. That's you can see now we are having approximately 386 gigawatt in which renewable energy sources is now keep on increasing every time. Every month, if you are going to see and update the data, you will find there will be significant change in the renewable energy sources. Also, you'll find that the various sectors, as all we know, that's like state, central, and the private sectors. So now earlier the private sectors were almost zero even in the 70s. And after that, you can say this share has increased and this percentage is approximately 50%, that is 48%. So you can say it is a keep on, we are moving in certain directions where to have the green power. And also this has facilitated to go for the smart grid. If you see in our country, the major contribution of the renewable energy sources are the two, that is a wind and solar. And solar is massively increasing, as we all know. That's here you can see that you can say the 44.69% is a solar, which is a grid connected. We are also having, even though there is a standalone, it's not grid connection here. And if total renewable energy sources, you will see it is approximately the 100 gigawatt. And still we are keep on moving. Every month this data is keep on being updated and we are increasing in the renewable sector more and more compared to other sectors. So some of the recent concerns that is happening across the globe, which have basically given our motivation to go for the smart grid, that we are having the limited expansion of the transmission network as compared to the generation addition. We have to add the generation because the demand is increasing. Once the demand is increasing, we have to go for the generation, as we all know. That generation should provide all the loads without interrupting anyone. But at the same time, the generations, many generations, those were added maybe the 40 years before, they are also still in our system. And we have exhausted their life, but they are there. Most of the generation and also the transmission lines, many of the transmission lines are more than 40 years old. And they have become old and sometimes they're getting a lot of problems as well. We are having a lot of transmission and the distribution losses. And in the transmission, I cannot say the more losses we are having at par with the international standard, but the distribution losses are very high, both technical and the commercial. The technical means the conductors are basically overloaded in the distribution sectors, and that's why I square R loss and other losses are there. And commercial, we all know why these losses are there, because we are unable to collect the revenue from the various ends. Also, we are not having the proper data, that is the dynamic data, about the health monitoring and the control of our devices, operators, like the transmission line, transformers. What is the condition right now? Every day it is running and suddenly it is burnt. And that creates a lot of, even though, interruption in the supply, and also a lot of other problems are occurring. Increased concern toward the vulnerability, because the grid is keep on adding, we are keep on making complex and complex. So the resilience of the system under the natural and man disasters are other concerns. So we want our grid should be resilient, so that we have to use the technology for that. And the communication and other technologies are there. We can already, even though a lot of other like devices like wide area measurement and other things are there, where we can make our grid very tight. As you know, the last breakdown, or you can say collapse, our grid was in 2012. Before that, it was 10 years. So our grid is very well operating, but still always there is a concern that we should still go for the better way. Environmental concern, we all know that we are unable to, even though, generate power from the coal, and also the dams construction, etc., are basically stopped or delayed due to the various agitations. So these are the another concerns. And as you know, the power quality is one of the concern, in not only in terms of reliability, not in terms of the voltage variations, not only in terms of frequency variation, but the addition of the power electronics devices. They are basically trying to make our signal non-sinusoidals, and that is basically creating a lot of, it is alternating, but we are having various other components. Those are coming like notching, flickering, sags. Well, many type of power qualities are also now going to be another concern due to the more and more addition of the power electronics device in terms of converter. They are very good for the system performance improvement, and they are being used, but at the same time they are creating some of the problems. So those are concerned. And another, just we have to meet the ever increasing electricity demand. So our present power system was basically heavily relying on the fossil. Still, you can say it is more than approximately 60% relying on the fossil fuels. We are having the AGC like generations. Load is in control, because the loads are not the price reflection. So it is they are using the demand whenever they want, and the generation is basically following it. Limited ICTs are in beginning, but in the future, or you can say when we are talking about the improvement or smart grid, whenever we are talking, we have to go for more and more renewable energy sources, clean coal, nuclear power, and the load follows generation. Now you have to use your load depending on the price, and that is now going to end. It is giving the birth of the competitive electricity market. So that is going to come, although the individual customers are not very much affected in our country, but across the globe it is happening. In our country also, the price is 15 minutes, it keep on changing, but it is reflected in or not in our bill, because it is taken care of with our corporations or wherever, who is your supplier, they are doing on your behalf. And we have to go for the digital technologies. We have to use more and more ICTs, smart meters, so that we can have the smart grid. So at the same time, that those were the concerns, but at the same time, there's a lot of technological changes happening in the electricity sector. And the first technological development is new materials. It may be the polymers, it may be your composite, nano, and the superconducting material. Due to this, the size of insulators are going to be less, machine sizes keep on increasing, and also the rating of machine is increased, just we can find. Also, already I talked about the alternate and renewable energy sources. That is also we are using where to address the global environmental concerns, improving the energy security, reduction in T&D losses and requirement. Development of new technologies like smart converters, flexible AC transmission system, power quality conditioners, DSP, sensors, smart metering, they are basically also being widely going to be used, and they are in the place in the various sectors as well. So intelligent control using the artificial intelligence, machine learning, these are also going to be used in our electrical system. Information and communication technology like IoT, Internet of Things, machine learning, blockchain, all these technologies are also going to be put, and they are basically going to be in very massive way in the future. That's why whole our energy that is going to be changed from the digital. We are saying the digital energy transformation. We are for maintaining the security, reliability, and resilience of the large interconnected system, that is WAMs, SCADA, distribution automation, etc. So all these things are already in the place, but the WAMs are also used for the interconnected transmission lines. And no doubt in the distribution sectors, this is the power quality issue, the smart grid, microgrid, and they are basically now the future, which is we are talking, and that we have to give the solution to the challenges and to make our grid more and more smarter. And of course, the regulatory changes which are happening, that is a customer value added services across the, and also the cross-border trading. We are having the trading with the Nepal, Bangladesh, Bhutan, that is also being happening because the pricing difference or the timing difference, they are there. And we are operating in the unregulated price-based operation. The regulatory tariff, what we are paying, it is regulated by government regulatory commissions. But the higher end, when it is a bidding process are there where the price is uncontrolled and the price is decided by demand and supply. So the future grid, I say the smarter grid, because the smart grid, is not absolute. It is to keep on improving our own grid to make and achieve certain objectives. Always we say the smarter grid. A smarter grid, we are using the wide area monitoring system and control. We are having coordinated whole energy management system and the full integration of the DG with the large central power generation. So it is not only the energy related to your power generation, but energy related in transport. Other sectors also, we have to have a very coordinated way, so that's why electric vehicles is, you can say, they are coming on the roads. So all these things are required in the smarter grid. Extensive, small, and the distributed generations close to the end users. We are now trapping the power wherever they are available, like solar, it is very near to where you are located. And that is basically also used, if the wind is there, that it can be also trapped. So the secure, reliable, and green power should come in whole our power. The customer-driven value is very, very important. Actually, just this example, if the power supply goes off, you just talk to substation, nobody will attend your phone. But now the customers are aware and they say that I need this my services. I should know when I'm going to get my power and when I'm not going to get the power in the case of interruption. Harmonize the legal framework along the cross-border power trading is also important, which is happening. So these are our future grid is going to be the smarter grid, and we every corner we are doing. Again, up to what level we are achieving, that is always keep on improving depending on the large and very old system, and those concerns already I talked. So using the digital technologies, we are also moving further, and a lot of projects and other things are working about the digital energy transformation. That is, the changes are being driven by the three powerful technologies. One is the emergence of digital technology, including the Internet of Things, artificial intelligence, machine learning, the various type of computing, like it is a cloud or whatever the computing, just and the blockchain, etc., are going to play a very vital role. And the arrival of the increasingly affordable distributed power technologies, like you can say the solar. Earlier, maybe 10 years before, it was the 20 rupees. Now you can say it is a 2.5 rupees. That is, a price is going to be very low. And also we are having the better operation and control strategy. So that's the distributed power and the decarbonization through the renewable energies and the energy efficiency options. We want the low carbon technology, that is the concern. So the 3Ds are basically main focus, which is transforming our electrical system in the digital transformation. That is the digitization, where the addition of intelligent control systems, internet-enabled software to optimize plant and the grids, decentralization, like a distribution of the small-scale generation throughout the T&D, decarbonization, already I talked. So these three are the very, very important things which is happening, and that is going to happen. So this whole then digital energy implementation, where we going to be smart grid, is basically it is further we are moving that directional. First we have to smart grid, then we have to have a put more and more all these things. That is all, because you can say only the different words we are talking. So it's the challenges that is there, that I'm opening the various questions. This will be my last slide. That increase in the operational efficiency. It is a lot of, you can say, the generations having the low inertia, no inertia, nature dependent, when it will be off, when it is on. So this complexity is going to increase. That's why we need a very sophisticated control system. We need a very good information system. We are having a huge data. That must be basically data mining and data things to be analyzed, because there will be a lot of dispute, since it is a market oriented. Once we are talking who is consuming at what level, what was the price, whether I can shift, I can get some incentive or not. And it is basically more and more business is going to be involved in that. So the huge business potential in the electrical market as well now going to arise. Earlier it was a few generators, few transmission companies, few distribution companies, and it was in the very few. And now it is going to be anyone can play in this field as well. We require the information in the cyber security, because once you are having everything is on IP and the digital, so then you require all these things. We have to have the very cost-effective implementation, because the cost, once we are putting all these technologies, the cost may go up. So we have to go for the cost-effective. Requirement of accurate forecasting approaches, because once you are going for renewable power, if you want to smart grid, your forecasters should be very good, so that you can very easily manage your grid in the very efficient, economical, and you can say sustainable part that is achieved. We also ask the demand response that people can respond to the price, and that is also people are going to the price signal must be given, and based on that people can respond. So the demand response will save a lot of our energy and money because the peaks are occurring very few hours. We can valley filling and that other responses. So many things are happening. You must be knowing this. We have to redesign our market in such a way that it's small this company where they are nature dependent, like the solar, like wind, they don't know what is after 1 hour whether wind and solar will be there or not. So that design the electricity market is at lower rent so that they can make more and more profit. And as you know, in our country we are having the solar and wind certificates along with the capacity as well as energy, both are delinked and they are treated separately, and that is mandated by the regulatory commissions. So that is already there, but still we have to go a long way in these directions. We require fast analysis tools, everything. Now, whatever the things you have known, that is even the short circuit using in the power electronics says what will be the short circuit level, what will be their load flow, how fast you are forecasting, how fast. So all the things should be very fast in these days. And we have to have the integration of renewable resources. We have to tap this. They are having the low inertia, how to handle that. If it is a huge surge, use power on and off, then it will require a lot of problem in the grid disturbance and the power quality. So many more issues and challenges are there. No doubt we are having and we have reached certain solutions, but still there is a long way. A lot of potentials are there so that we can basically handle this. So it is basically just I want to say this all together about myself. So thank you, and let us listen other speaker.
Thank you, Professor S.N. Singh, for your insight into the topic and mentioning the challenges what the electrical engineers supposed to go through in the present day situation, managing the renewable energy because it's so uncertainty and it has to be managed well. Then growth of electricity in India, limited expansion of transmission network, T&D losses, poor power quality. Also, you have briefed with the advancement of technology, namely starting from materials, increased use of renewable energy, and advancement in power electronics technology, digital controllers, and AI techniques, etc. Also, digitization and decentralization techniques will help in overcoming all the problems what we are having at present. So thank you, Professor, for your short and crisp presentation on the topic. So now I'm extremely happy to introduce Professor Cipher Rugman. So Professor Cipher Rugman is the founding director of the Advanced Research Institute at Virginia Tech, USA, where he is the Joseph R. Loring Professor of Electrical and Computer Engineering. He also directs the Center for Energy and Global Environment. He is a life fellow of the IEEE and an IEEE Millennium Medal winner. He was the president of the IEEE Power and Energy Society PES for 2018 and 2019. He was the founding editor-in-chief of the IEEE Electrification magazine and the IEEE Transaction on Sustainable Energy. He is the founder of BEM Controls LLC, a Virginia, USA-based software company providing building energy management solutions. He has served as the chair of the US National Science Foundation Advisory Committee for International Science and Engineering. He has published over 115 journal papers and has made over huge number, 600 conference and invited presentations. In 2006, he served on the IEEE Board of Directors as the Vice President of for Publications. He is a distinguished lecturer for the IEEE Power and Energy Society and has lectured on renewable energy, energy efficiency, smart grid, energy internet, blockchain, IoT sensor integration, etc. He has a PhD in electrical engineering from Virginia Tech. So I also extremely happy he visited our institute, National Institute of Technology, Tiruchirappalli, for the National Power System Conference, NPSC 2018, as the chief guest. So now over to Professor Cipher Rugman. Professor, I think you have to unmute.
Can you hear me now?
Yeah, now it's clear.
Thank you very much for the kind introduction. I also want to mention here, Professor Singh did an excellent presentation. He has done half of my job. He has introduced the smart grid very well. I will not focus on that part. That will save me some time. Also, you may know, Professor Singh is running for IEEE Power Energy Society Secretary. And I am making a strong plea to all of you. If everybody in India, in PES, votes for him, he will win the election. Keep that in mind. So you have an obligation to support somebody that you know very well. So having said that, let me move to my talk. If I can get the full screen. Hold on a second. Is my screen visible now?
Yeah.
Okay, thank you. So I'm going to focus on the smart distribution part and show how that distribution being smart can help to integrate more renewables. That's the objective in the next 15 minutes. This is how I see what I call the smart grid ecosystem. Ecosystem starts at the smart building. I'll tell you more about that in a few minutes. What's the smart building? It has intelligent building automation system, smart devices, productive users, and can be connected to the grid directly. That's the smart building. A collection of smart buildings makes a microgrid. Then if you get many microgrids interconnected, that's part of your distribution system. And then at the very end, you have the smart grid, which allows bi-directional flow of energy, meaning in a building, you can buy power from power company. At the same time, you can sell power back to the power company if you have rooftop solar producing more power than you need. That's the big picture. That is what I call smart grid ecosystem. Now, how can a smart distribution grid help? Smart distribution grid, SDG, is a part of the smart grid, as you just saw. This SDG connects the supplier, the power station or bulk power supplier, to the end user, which is you and me, so the electricity can be delivered more efficiently and more reliably. So SDG is the linchpin, is connecting the supplier to the end user. At the same time, we know the smart distribution grid hosts much of the distributed energy resources, your local battery, local rooftop solar, some small wind turbines. And to me, a distributed energy resource also electric vehicle. Why? Electric vehicle has battery storage, and at the end of the day, you may not have used up all the stored energy in the battery. So you are becoming a source now. If you can hook up that battery in your garage or in your office building, it can send power back to the grid. That is why the car is a energy resource. We'll talk more as we go forward. Now, let's focus for a minute or two on a smart building. To me, any building can be smart. You don't have to build a smart building to start with. In the US, there are about 6.5 million commercial buildings. 90% of those are more than 15 years old, 90%, and they are not smart. Does it mean we cannot use them as smart buildings? We can, by putting some technology in the building. What has to happen, if you look at this building. If you want to make this building smart, it must have something fundamental. You must have a single platform which can monitor and control heating, ventilation, air conditioning, lighting, water supply, sensor networks, security camera, fire emergency. All those can be added after the fact, one at a time, no problem. But all of them have to be controlled from a central location so that we can take advantage of, as Dr. Singh said, different pricing opportunities to make things work better. I can talk more later on if you like. Now, that was a smart building. And you see my smart grid ecosystem. From a smart building, I go to microgrid. It's a real picture. I work with a company called Comet in Chicago. They have built a microgrid, which is in Chicago. They call it the Bronzeville Microgrid. That has 2 substations on the left-hand side of the screen and many types of building, residential customer, science academy, battery storage, police headquarters, some library, National Institute, College of Optometry, nursing center, military academy, all of this common city setup, public library, solar PV, and some local generation. That's a microgrid. It has the exact numbers, about 10 megawatt in this microgrid, 10 megawatts. They have 2 substations bringing about 4 plus 4, 8 megawatts from the grid, and remaining 2 or more megawatts supplied by the local generation and rooftop solar. This is done. They are connected on the upper right-hand side to the Illinois Institute of Technology, also another IIT. They have microgrids. These 2 microgrids are interconnected. That's a distribution system. So you got a smart building, microgrid, then smart distribution network. That's happening today. Now, what is the challenge? Because our landscape is changing. It is no longer a large coal-fired power plant supplying power over long transmission lines to the city. No longer the case. You now have local wind turbines, rooftop solar, battery storage, and as I said already, electric vehicle. So this is the situation today. This is happening at the distribution level. We have to absorb all of these, control them, making sure they're operating in the most efficient manner. This is the challenge. And this is how I believe a smart distribution grid can be of help. Look at this. This is my building at Virginia Tech where I work. I put rooftop solar in this building just to see how the output load shape of the building match or does not match with the solar output. That was the objective. If I look at data for my rooftop solar, just look at a day which is a partly cloudy day, a lot of intermittency. This is fact of life. So challenge is, how do I deal with this intermittency? This is my supply. Supply changes all the time. One factor. If you take a better day, like this another day, more sunny still, clouds move in and out, have intermittency. How does a smart distribution grid help deal with this? That's the challenge. We'll talk about that as they go forward. That is solar. Let's look at wind energy. This is real data in Texas, wind farm, 150 megawatt wind farm. Look at this data about between 5 to 6 a.m. on a given morning. The load drops by more than 30%, from 140, 135 to more like 80 megawatt. In 43 megawatts in 1 minute. That much is your supply dropping. Imagine what will happen to the load serviceability if you depend primarily on the wind. Difficult case, right? That's one case. Second example, more severe. Same wind farm, different day. Between about 6 and 7 o'clock, the supply dropped 113 megawatt out of 140 at the time. This is a serious case. Again, after a couple of hours, you got a rise of 106 megawatts in 10 minutes. This is the reality, how you deal with this. So this is the summary. We have distributed generation. We know, we just saw that Wind and solar are intermittent. We know that, we have seen that. Hydro may not be intermittent, but you may not have hydro inside a city. There's no hydro in New Delhi, for example, but there's hydro in further away. That means, in summary, even though these resources, air, sunlight, water, are free, but they are not always usable. This is the challenge for the engineer to make it all work. So this is what I see is happening. I call it a new paradigm for the power system. Historically, we say demand-driven supply. You forecast demand for the next 10 years, build a power station to meet that expected demand. Fine. You are running a economic dispatch, you have to forecast demand for the next day, and based on the expected demand, you will schedule your power plants. That's what you call demand-driven supply. Demand is the independent variable, supply catches up. But now, your supply, you saw Dr. Singh's page, you got more than 100 gigawatt of wind and solar in India now. That's no guarantee. It can change any minute, it does. That means if your supply is kind of flexible, you have to be smart. Can you make your demand adjust to some extent to take care of the supply variability? What do I mean by this? I have done this research. I can see my lab has that work. I can, if I have rooftop solar, is changing intermittently because of cloud movement, I can control some load in the building to make the supply and demand match as much as possible without using a lot of batteries. How I do this? I can dim the light in your classroom by 20%. You will not be able to tell the difference. You can't tell the difference. 20% reduction of intensity of light. That translates to about 12% reduction in kilowatts. That's one example. I can raise the temperature setting on your thermostat in your office building by 2 degrees C plus. You will not feel any more discomfort. That's what I mean by smart demand adjustment to meet with changing supply. So that's what I mean here by saying supply driven demand. Demand has to adjust to supply changes. That's again my smart grid ecosystem. Now, this is how I see things happening in the future. Again, in a city like Delhi,
Hello.
I have been, yes? Hello?
Hello.
Can you hear me?
Yes, Professor, you can continue.
In this case, I am showing you multiple microgrids. On the middle of the picture on the top, I have one microgrid connecting 4 or more buildings. Each building has rooftop solar and some buildings have electric vehicles. That's one microgrid, part of a distribution system. And the modem-like picture in the middle reflects the telecom connectivity between all the loads in the system. That's one. On the upper right-hand side, we have another microgrid, which has some battery backup in addition to rooftop solar. The big microgrid in the middle is connecting the other microgrids all around. And this is also connected to the wind field on the left-hand side and a central station power plant on the lower right and other big factories in the system. Point is, you cannot have a microgrid serving everything. It's too big. You saw the Chicago Bronzeville Microgrid. It's part of the city, that's fine. So in this case, I have some battery set up, inverters, like the bottom microgrid, it has batteries and so on and so forth. Point is, in order to make the system smart, you cannot make the whole system smart at a time. It's not possible. What has to happen over time, you pick up a part of the city and deploy the smart grid solution in the city for that section. Learn from it, develop the hardware, operating principles, train the engineers, and then slowly branch out. So this is what I see will happen. I call it the smart distribution grid is a set of intelligent interconnected microgrids. You'll have sensors, solar, wind, battery, all the stuff will come together. That's what I think will happen. Now, how is the grid evolving as a result of these requirements and these expected changes? First of all, before the smart grid, which is the case in India and the US and many countries, the upper half of my picture on the screen, I have a central station power plant, step-up transformer, goes to the long distance transmission lines. The electricity comes to your neighborhood, step-down transformer, then goes to low voltage, 408 or whatever, 11 kV, goes to your street and serve your house and building. That's normal. What is happening now after smart grid, if you look at the bottom half of my picture, I have storage battery, electric vehicle, I have rooftop solar, I have wind power. In addition, I have large power stations. No matter how much we want to decarbonize today, it'll take at least next 30 years or more to get rid of all coal-fired power stations. It's not going to happen in India soon. So we accept it and work with it. That's the vision for the future grid, which we will call a smart grid. But that cannot be achieved overnight. It has to be step by step, learn as you go. One new thing in the bottom half of my picture, the blue lines, those are not power lines, those are telecom lines. That means every load, every substation, every supplier has to be interconnected in the smart grid. Now, so what that means, I have to merge power flow with information flow. So I have to have integrated communications. Look at this picture. That's what I call power infrastructure. You saw this already. Central station power plant on upper left, step-up transformer, transmission line, coming to your neighborhood, distribution substation, may have a gas turbine. I showed in Chicago as gas turbine. Distribution substation, that substation has parts. It has micro turbines in some cases, rooftop solar, batteries. If you go down vertically down, industrial load, it may have cogeneration. If you have like a textile factory, they need steam. They may have a boiler to make steam, and as they make steam at high pressure, that can turn a turbine, make electricity. That's cogeneration. Commercial buildings may have flywheel, fuel cell, all that is possible. That is our power infrastructure. Superimposed on this is the information infrastructure. This is the set of red lines, arrow left to right, top to bottom. Why is that important? Because we have to provide two-way communication between the end user and the supplier. That's the network or telecom network we have to have. So that's the overall picture. Just to give one example how it works. At my house in Virginia, I have a smart meter. How does the power company read my smart meter? Power company has provided mesh microwave network in the neighborhood. The 150 or so homes are sending data over the mesh microwave network to a data concentrator. That's power company's device, data concentrator. Many data concentrators are sending data to the local substation over the GPRS, local telecom wireless network. That's not power company's system. That is borrowed or rented from the telecom company by the power company, GPRS network. When the signal reaches the power substation, it travels to the control center via the power company's own fiber optic network. So fiber optic, GPRS, and mesh microwave. That's telecom network. This is happening today. So this is it. I have given you my email address. If you have questions after the session is over, my website is here, more data information there. As Dr. Singh said, election for IEEE president is going on now. If you have not voted, please vote. And this is what the election website is, IEEE.org/elections. So I'm going to stop here, Dr. Narajan, and I would now go back to you, and you can take the control.
Yeah. Thank you, Professor. Seeing is believing. So you made that excellent presentation. with real or practical system, and it's working across the country. So it's a very nice presentation, and as part of the presentation you brought everything: electrical, electronics, communication, and electrical engineering. It's supply driven demand now. Earlier it is generator driven, I mean load driven demand. So it's very good presentation. Also you brought out that merits and demerits of distributed energy sources, how we can make it for our advantages, and smart smart grid ecosystem, smart grid distribution system, microgrid, smart building, and so on. All are now we are seeing it's becoming a reality. Thank you, Professor, for your excellent presentation. Now, Mr. Sandeep. Mr. Sudeep?
Yes, sir.
Yeah, is the Rajamani is engineer
Yeah,
Rajamani is
yeah.
yeah.
Yes, sir. Yes, sir.
You
You can
want to
request.
yeah. Now may I request Engineer Rajamani, Chairman, Electrical Division Board, to say a few words about this webinar.
Sir, please unmute yourself.
And in the meantime, audience participants can give the questions.
Rajamani sir is not audible.
Yeah, he is not audible. Sir, you are not audible, sir.
Your microphone is not showing here.
He has
Rajamani,
not
sir?
been connected. Now it is.
Yeah,
Hello?
now connected. Yes, sir.
Is my voice is audible to you, Kumaresan?
Yes, sir.
Yes,
Yes,
sir.
sir.
Yes, sir.
So you have arranged a wonderful meeting. It is a very informative and it is an exposure to the practicing engineers. But our practicing engineer has not participated in most of these, and this we will have to communicate it to all the centers to so that it will be communicated to the practicing engineers the methods they have adopted in USA, and what we are doing it not in a smart city, that they are doing the smart city covering an entire city, you know, but we are doing without only in smart metering. That's all we are doing. We must also improve our smart metering concept and even exposure with communications. That is my inference from these things. Thank you for the panelists. Thank you, Mr. Sabri Rahman, and thank you, Professor S.N. Singh, for your elaborate informations. Thank you so much.
Thank you, sir. So now I think we can take few questions from the audience. Already one question is that, so efficient power transmission is DC or AC, and what extent? So Professor, who would like to give?
Dr. Singh, you can take first.
Yeah.
I'll follow you.
Okay. Whether AC or DC, which is the best, all it depends upon what is the power you want to transfer and what is the distance. As you know, there is a lot of advantage in the DC transmission because, as you know, we can go for the longer distance transmission without any power compensation. In the AC system, you know that we cannot have more than 500-kilometer lines without any substation and the compensation in between. But in the DC, we, as already know, in India, we are having the one very big DC that is coming from the Vishwanath to Agra by Alipurduar, and that is approximately 1900 kilometers. But in the AC transmission, this is not possible. So if you want to have the bulk power transfer, because the terminal equipment's cost is very high in the DC. No doubt the cost has reduced drastically due to the power electronics advent, etc. But still, the break even just normally you go for the AC and DC, it is approximately 600 kilometers still. So if you are having more than 600 kilometers, you have DC is always advantageous. If you are going for lesser, then you can go for AC in terms of cost. But apart from that, the DC gives many other advantages. like you can control the power. Suppose you want to connect the two states, two regions, two districts, two countries, then the DC is the better because the power can be controlled. The fault or disruption in one area cannot be transmitted to another area. So many advantages. So it depends what you want. If you are going for lower voltage, it is AC is still better and the distance is less. And that's why even the people are now debating in the smart grid or microgrid, whether it's the AC microgrid or the DC microgrid. So people are still debating, but already our infrastructure is AC in that, because the power electronics devices, they are the DC. Always we are AC, DC, we are keep on converting. So if it is that, so people are working, and it was found that DC is better than in the microgrid, lower voltage also. But changing whole infrastructure, changing whole your socket and operators and other standards, that will be expensive. But if you want to develop new one, that you can go for. So now it is to Professor Cipher Rugman, please.
Thank you, Dr. Singh. Very good explanation. I will not repeat what you said. Just to add to what you said, there is talk now at the distribution level, local level, is DC better than AC. Why is that issue coming up? Most of the load, all your computers, all DC, all DC. Today, LED light is DC. But what happens? If you buy LED lamp, it is a converter. It takes AC, makes DC, and the cell for the lamp is DC. So why do the conversion? But we have no infrastructure to bring DC to my house. It doesn't exist. What I think will happen over time, I know in China, they're building a DC substation. DC substation is happening. Parts of New Delhi, the TPDDL, they can have a part of Delhi area provide DC supply. Just test it out and see how people pick up. You have all your LED lights, equipment, all DCs. I think happening maybe 10 years from now, you have a choice now in your home, DC supply, AC supply, and build up on this. As Mr. Rajamani said, engineers have to hear this, and they are the ones who make it happen. Engineers, power guys, very conservative, very slow change in our business. I'm hoping they will be more open-minded and try out new things. I'll leave it at that for the engineers to think about. We can talk later on if you like. Thank you.
Again, I'll add, Professor Rugman, because you talked about the load side is a DC, and we are having many DC loads. Even though fans are also BLDC motor-based loads, air conditioners are also coming with the DC. The converter are smart inverter based. But in the generation side also, you can say the fuel cells, solar, even the wind, if it is a full converter based, that is also DC. So now the question is, if we are going to have the microgrid where their generators are little solar based, why we are going to convert to AC and connect again, go back to DC? So many things are coming into the picture, but only you have to see the power handling capability. Voltage drop, because I square R, as you know, and IR. In the transmission AC, you can, even the voltage can be controlled the load center as well. So, but nowadays the converter with the capacitor, that also capability we can give. So it is a very challenging task, and the future, hopefully, we'll be having some sort of, right now we are the mix AC and DC, but the future it may be the DC microgrids, and that is a more advanced. Suppose you are developing fresh, you can go for the DC. Thank you.
Yeah, thank you for a wonderful answer reply. So now I guess that next question is to Professor Cipher Rugman. What are recent implemented projects in US towards the self-healing concepts? Self-healing concepts of smart distribution grid. What is the communication channel used? What are the challenges and the learning from the pilot projects if implemented so far?
Now at the microgrid level, two things. One, power line carrier, PLC, is commonly used. Because if you within the same transformer, you have no issue with the PLC traveling across transformer. That's one. But as I said, in my case, my smart meter at my house is talking through 3 channels to the power station. First is mesh microwave. That's one, few megahertz, to the data concentrator. From there, it's going to the substation over the GPRS mobile phone network. And then from the substation to the control center of our company, going over the fiber optic line. It's not one, it's many things, depending on the cost, availability, and so on. Power company, in my judgment, will never build a full-scale start to finish their own telecom network. It's not cost effective. So they'll depend on the commercial supplier. In Europe, they think differently. Europe is focusing more on power company providing full start to end telecom network, which they control. Security issue. So it's a matter of security, cost, best practices. The answer is no one answer. PLC is widely used within a microgrid, but GPRS, mesh microwave, fiber optic will also be there.
Yeah, thank you, Professor. Thank you.
Yeah, I'll add in what we are doing in my campus. Already we are having the complete distribution, smart distribution system. And the meters are there, smart meters we are having, and we are having even the solar on the rooftop of all the residential buildings. It's a small 5 kilowatt. And we are using the local area networks as well in IP based. And because already we are having the telephones lines in the same telephones line, fiber optics cables are there in whole campus. From there, we are taking to our substation. But many times, a lot of problems are still happening. Many times, data is not going. There is a lot of packet drops. Many issues are there. So that's why I said in the very beginning that we have to go for the very cost-effective. The ICTs are important. And if you are going for very expensive, no doubt mobile, you can have the mobile network. It's very expensive. If you are going for the Wi-Fi, distance, line of sight, many other issues. So all the things people are communication guys are working in this area, but it depends upon what infrastructure you are having. Already we had the telephone lines. It was on the fiber optics. Same line is used for the communication also we are using. So there is a meter, IP is connected, and finally going to our substation where the data is recorded. But what it is happening another is we are not taking the data at the same time. We are having some storage capacity in the meter also, because if there is any problem, it can store some data and that packet will be going. But once the data packet is going, there many packets are lost also in between. So the complete data is not there. In my house, I asked, give a complete data. They said that some data is missing still. So that you can say this is happening in our country, just I can say.
Yeah. So thank you, Professor Yasin Singh, for your wonderful answer on that. And I guess this is the continuation of the previous question. In smart grid, we have to deal with bidirectional power flow. Is there any separate plan for setting up logic for restricting reverse power protection in case of the consumer location in smart cities? So in smart cities, I think that the question is there any protection scheme for taking care of this reverse power flow?
The two answers to that question, one at the end user level. Right now, in many cities in the US and Germany as well, they're insisting on what they call smart inverter. Why is that an issue? That's the following situation happening. Seen data in San Francisco, PG&E power company, San Diego area also. Mid-morning, 10 o'clock or so, San Diego especially, the fog burns off, sunlight strong, people not home, demand is low, so the solar is producing a lot of power. That power is going to the local distribution network. What is the result? Voltage goes up because of excess supply. The regulation in the US says voltage must be maintained plus minus 5%. This 110 volt can go up to 116, 120 becomes 126. That doesn't matter, plus minus 5%. With the excess solar, that is going more than 8%, 9%. So what the power company does, they shut it down, the inverter, shut it down, don't take any power. As a result, the homeowner not getting any benefit because they could sell the kilowatt hour. What a smart inverter does, it allows the power company to change the firing angle, cosine theta. You know, power is VI cosine theta. So if you change the cosine theta, voltage and current can be adjusted. That way they can get 80% of the supply, not 100%. So the homeowner can sell 80%. That's becoming good practice now at the lower level. Reverse power flow is reverse power flow happening, right? If you have too much reverse power flow that is going to go across the transformer to the next feeder to protect it, they are now putting reverse power flow barriers at the transformer level so that the excess power does not travel to the next circuit. So that's what my answers.
Yeah, thank you, Professor. So I guess that the other question related with cyber security and security threats in smart grid is a prominent area of research. Kindly comment on this.
What is saying? Can start?
Yeah.
Cyber security and
yeah,
security threats.
I think all these things already I told my last slide about the challenges where the information and cyber security is very, very smart issue. Because once we are talking about the IP based, we are talking, suppose you are using your appliance like, for example, washing machine, and you want to start your washing machine sitting in the office, then you have to use some internet. And from here also you can operate. And once you are using internet, then there is always the hacking and lot of problems will be there. People can furiously, without even intention, that can be on. Your AC can be turn on, turn off. So whatever if you are going for more and more internet base, where this is always there. Even though our operation, for example, the large power system, where is the computers and we are the control centers having all the communication by maybe you can say whether the GPS based and already the communication channels we are using. And that communication once you're using, if it is hacked, whole grid may be failed. It is one from the consumer end also it is a very dangerous. And also at even the large power system also it is a very dangerous. That's why we want to say there is a cyber physical system. Our system is a physical, but it's operating with the information and communication technologies. And that's why it is a cyber security is very, very important. And that's why a lot of people are working towards this, that how we can make and how we can have the various level of protocols, layers, and to control and save our grid. Even the small disturbance, as you know, maybe the traffic suppose signal is gone, no problem. Even the train signal is hacked, train will be start for a certain time and it will be started. But in the grid, if it is a fraction of seconds of disturbance is there, whole grid will be failed, not only that line. So a lot of things are happening, and that is basically it is our important aspect and it is running. But at the same time, we are going very cautiously, we are going very slowly, so that these issues are also parallelly tackled, and that is basically there. When you are going by more and more communication, more and more these challenges will be there. Thank you.
Yeah, thank you. I think next question, it's given in the presentation. Will energy storage will be key requirement to handle fluctuation in renewable energy sources? So I think the answer is yes.
Yeah, that's my point. You can have what I call a brute force solution, brute force. The lot of batteries. That's not good. It's expensive, and batteries take up space. And batteries have to be cooled as well. You can't put a battery in the sun for too long. So what I'm saying, in addition, we have a problem. We have fluctuating supply. We know that. We cannot control it. Deal with it. Don't use battery alone. Make your demand smart. As I said, I can adjust your light intensity by 20%. You can tell the difference. So play with that game. You need some hardware, of course, in the building to make that happen. So my point is, be smart, look at the demand flexibility, look at the demand variability, and I can forecast within 3% accuracy the solar energy for the next 2 minutes. I've done that. 2% accuracy. If I know the sunshine is going to be this within the next 2 minutes, I can make some pre-arranged controls of my air conditioning load, a large fan, ventilation fan in the building, my lighting circuit. It can be done. It needs some hardware. Sensor technologies can be done. So my point is, be smart. Don't be a brute force solution provider, and you can do much better. As a result, building becomes smart, and it can save you energy at other times as well.
Thank you, Professor.
Yeah, I'll add here what Professor Rahman told. He's very rightly, because the storage is going to play a very vital role in where we are having more and more renewable energy sources on the two aspects. Because most of the renewable energy sources like solar, it has no inertia. Even though we are having wind, very limited inertia, because we are having no doubt certain kinetic energy rotation, but using the pitch control, etc., we can happen. We can have the virtual inertia, we can have some control philosophy, but virtually we don't. And also these are the nature dependent like wind and solar. It is not in our control. That's why they are known as the non-dispatchable generators. Because if you want to increase, you cannot, because already you are tracking and you are trapping the power at the maximum, you know, MPPT algorithms are there. So reduction is possible, you can switch off, no problem. But if you want to increase, it is not possible because the laws are not there. So the forecasting is one issue. No doubt the forecasting for the limited hours or maybe hour ahead, etc., is very accurate. It can go up to 5%. But if you are talking for a thermal power generator, if you want to be ready, even if they are in the cold roll state, it requires the 2 to 3 hours or 4 hours. And also if it is a cold, hot roll I'm talking, even the cold roll, it is a 5 to 7 hours. So at that time I should be prepared. So the forecasting, once you are going for the longer look ahead hours, the error is going to be more and more, because it's very difficult to say what will happen after 10 hours. But I can say what is going to happen after 1 hour. So that forecasting is going to play. But if you're having the storage, then you can very optimally, because that energy that you can start very quickly, because you are having the various type of storage. You know, the battery storage is one, but still that is very expensive if you are going for the large amount. So people are going for thermal storage. People are going for chemical. Even the hydrogen energy in India, it is going to be promoted very largely. We can make the hydrogen, and then from hydrogen we can use the fuel cells. We can generate electricity very fast and very quick. We can get the water also at the same time for the drinking and other purposes. So the hydrogen network, it is going to be formed in our country. And also it is going to happen in the European Commission. I saw many projects are going to be the hydrogen energy. If you are having the enough renewable energy sources, you can generate hydrogen and you can transport even. You can generate also. So that basically the different type of storage. Hydrogen is also a storage energy. So we can have the different type of storage energy, and people are working, even the thermal energy, compressed gas energy, all the things, mechanical energy also the people are talking. So these things are basically the very, very important. Like I know I worked 1 year in the Denmark. There's a lot of flywheels are running. The induction machine with the big flywheels are running continuously to provide the inertia, because in Balholm there's a 50% wind. So that's because any surge, if the inertia is not there, you can say the frequency deviation will be very, very high. So that storage is one of the big issue, and the people are working very hard. Which type of storage is good for our system? Is a cost economical also we have to see, and the losses should be minimum, and also efficiency and performance should be better. So that people are working and hope to get the fewer when the storage. Our even Bharat Ratna Abdul Kalam ji said in the one of the meeting, and I just read his book, he said the future may be surprises, that one day just like your milk you buy for every day, you buy the energy for every day. Just bring a socket and put in your house, for 24 hours energy will be sufficient. At that time, there will be no wire, nothing, and we electrical engineers will be jobless at that time, I hope.
Okay.
So surprises will come. It may not love, sir, it may be future. I don't know the results, anytime it can come.
True. Many things are coming true, because even
many good researchers came by the surprise only.
People say that they want to put the solar plant in moon. So today it may be that imagination. We don't know what will happen in future. Yeah. So next one will be of very specific questions. What are the techniques used to locate the fault in smart distribution networks in India and the US? I think if
from the same time,
you see the fault locations, the various type of algorithm. One is the very conventional, based on the you can have which type of fault you are talking, because we are having the data all the time. And if the data is, suppose you are talking the distribution system, you are having data, transmission system, we are having data. Based on that signal, we can also get the information. Now people are talking the transmission line fault location based on the digital signal processing of the data which is received, because you are having the voltage measurement and the current measurement. Based on that, you can say the current increase, what is the current going to be there. So that there's a lot of analysis, a lot of even the NN base and other base people are using. Even though suppose there is a complete breakdown, then you can, if the fault is there, you can use the Megger, another thing you can measure where the location. But the fault locations are lot of techniques are available, both AI based and the conventional based. Based on the measurement data what you are having, based on that we can do, and it is basically now practiced everywhere. Thank you.
Yeah, what is possible now that was not possible 3-4 years ago? We have a lot more communication built into the network now. This new. Yeah. Communication. That means you can monitor the current, voltage, frequency, real time in the line, real time. As you monitor the current flow changing, you can see fault called incipient fault. Fault happens slowly. It doesn't happen suddenly. As you monitor the flow of current and voltage, you see fault is coming. And then before the fault occurs, you can take the action needed to either bypass it or shut it down. So that's possible today. It's not widely used, but there are hardware now you can buy in the US to do exactly that. But you must provide full telecom access to that end-use device.
I'll add here one example, which the grid failed, which 2012, where just you can see, based on that, how we located the fault, where was the fault and what was the region. It was having the two PMUs, one at IIT Bombay, one at IIT Kanpur. Based on those signals, we just analyzed in the fraction of a minute what was happening, how system was trying to restore, but it could not be. Where is the fault and what happens in the BNAB, the double line, one line was out. So all the things are basically now we are having the good number of communication, even though like every milliseconds we are having the data, and from there we can analyze and we can look at very clearly that what happened. Earlier it was not possible. Earlier, even though oscillations were happening, it was not possible. Where is the oscillation? Why it is happening? So nowadays we are having with the help of the data, that is basically very well we can isolate, we can identify the data, faults, etc. in the system. Thank you.
Professor, next few questions related to the smart meters. It's related with what is the technology they are using and what technology they will be using to reduce the cost. More or less 4 or 5 questions related to smart meters.
Cost reduction is an issue of volume, number one. For example, I've checked in Virginia, where I am located, a local power company to provide smart meter, it costs them about $200 per installation, 200. Meter costs about $30, meter itself. Use the traditional digital meter, costs about $15. So $15, $30, $200. Why 200? The bulk of the cost is telecom network, and maintaining it and providing it like mesh microwave network. That's new. That's needed because you have to serve the smart meters. So as the supply and numbers increase, you can bolt more and more meters into one network. So overall costs will go down, even though the meter cost may not go down by itself as much. Don't have to. That's one. Second is the meter technology. The meter today, we can buy in the US smart meter with Zigbee chip built in. The Zigbee chip talks to the Zigbee chip on a thermostat. Now the power company can send a signal over the smart meter to turn the thermostat up and down. Now, no new hardware needed, they're all built in. So as you spread the cost to provide more and more services, your value goes up. So I don't look at the cost as much, I look at the value. If you can do more with it, your investment is more cost effective. So think about the value part. One quick example, your telephone, rotary dial, we are not very old to know all of those. The black telephone, rotary dial, that for many years. That costs in the US about $12, $12. iPhone 12 costs $1,200. $12, $1,200. Nobody says make the iPhone cheap. No, iPhone gives more features, like, for example, WhatsApp, our internet. So point is, look at the value it provides so that you can spread the cost among many end users. That's how I see it.
Well said, Professor. Good. So I think this will be the last question from the participants. Wireless transmission of electrical energy, is it a reality? Since pilot in New Zealand was completed in a recent time, it should come reality. So Professor S.N. Singh, you want to comment on this?
Yes, you know, already people are having the devices that is known as the wireless charging, and where there's no wire, and finally there's some part of energy is flowing. Even though people are still thinking that the battery which is moving, if you can have something on top or it can be on the ground, it can be automatically charged. So that charging basically requires many things we have to think, because it is a field oriented. It is a high magnetic things are there. At the same time, since it's moving, a lot of reactive power requirement is another concern, because it is inductive charging. It is we are talking, and even though capacitive charging and inductive charging, a lot of people are saying again the risk is there in capacitive charging, etc. So for the bulk amount of power, large amount of power, is still it is a long way to go. Right now, it is for medium and small power, it is a feasible, but if we're going for larger amount, it is a very still risky. Just I remember just 30 years before, when I joined the electricity board, there was one project that suppose the 400 kV lines are going, why we are having why not we can have the inductive load if the village is just below this, remotely placed in the hilly area, why not I can take the power, and because this is a, there is a one turn and we can have certain here secondary, we can get the power. But again, the reactive power plays a very vital role, and finally this project could not be succeeded. So this is not a new concept. We are trying very long back that even without having touch with the 400 kV line, if the village is nearby, why not we can take, because its induction effect is there, flux is there always in that one. But it was not materialized due to again the reactive power and other issues in that one. So still we have to go a very long way to go for the large amount, for the small amount, because the carrier you are having high frequency where you can put the energy, that energy you can take. That is my say, but still I think long way to go. Thank you. Professor Rahman.
Just very quickly, 30 seconds.
Yeah.
This is all good. You may heard thing called satellite power system, SPS.
Yeah.
They're talking about putting a lot of solar panels in the outer orbit, no cloud there, and beam the power back to the ground. How do you beam it? Microwave. Issue is microwave is okay if it is not very intense. If you spread the antenna size very big, so the microwave per square meter is not very big. Say a bird flies through it, would not be killed. This is a plus and minus. Wider network, not intense, but a lot of money, build a huge antenna system. You make it a narrower focus, more intense, a bird flies through, a bird will be fried. It's a microwave oven, literally microwave oven. So this is the engineering and the plus and minus. So you hear this SPS, but take it with a grain of salt. It is not that simple.
Thank you, Professor. So,
Mr. Kumaresan,
yeah, please, sir.
I have one question. How is
Yeah,
the
please,
position
please.
of hydrogen generation at USA?
Hydrogen.
Electric power generation, bulk hydrogen.
Nothing much is happening because two reasons. One is hydrogen gas has to be distributed like natural gas to serve power plants. It can be done, especially if you use fuel cells, can be done. Problem is hydrogen is very highly flammable gas. It burns very quickly.
Explosive, yeah.
Explosive. This is the risk. The balloon that burned up in the US university many years ago. So that picture is people's mind. We have now in the US hydrogen powered fuel cell buses. The tank on the roof of the bus and highly protected. That's very expensive. So my guess is hydrogen based supply will take a lot of time in the US. It may go into fuel cell first, maybe PEM fuel cell for vehicles, but not bulk generation, not anytime soon.
Okay, thank you, sir.
Thank you, Professor.
Okay.
So, thank you very much. So, from my side, I think one last question. Now, we are thinking of exploiting and using more renewables. So, is it possible to operate that electrical power grid with renewable alone? Without
Answer
conventional
is
power plants?
a very good point. As Professor Singh said already, our system is inertia based. Large hydro, large coal provides rotating mass inertia. If you lose something quickly, the inertia in the system can take over it. It speeds up, slows down. If you have no inertia, no large machine moving, where's inertia? Now research is going on for inertia-free system operation in power electronics, and no inertia needed. But that work is ongoing. Germany is talking about inertia because their system is highly electronic based today. because of their large wind, large solar, and designed to get rid of nuclear in the next 8 years. So this is ongoing. It's no answer yet. It will take some time.
Yeah, thank you, Professor. So thank you. So I'm extremely happy that this program went very well, and I am very fortunate to have the eminent personalities like Professor S.N. Singh and Professor Cipher Rugman for discussing and honoring that IEI with your presentation process. Thank you very much, and my best wishes to both of you for IEEE election. Thank you.
Thank you very much.
Thank you very much. Thank
Advance
you.
congratulations.
Sir, vote of thanks by
Advance
Director Technical.
congratulations.
So,
Respected
Rajamani's business, it's advance congratulations to both of you.
Thank you. Thank you.
Congratulations, sir. Respected Chairman, Electrical Engineering Division, Mr. P. Rajamani, our most valuable invited speakers, Professor Saifur Rahman and Professor S.N. Singh, our esteemed moderator, Professor N. Kumaresan, ladies and gentlemen, it is my privilege to offer vote of thanks on this occasion of the webinar on Smart Distribution Grid. I would like to express our sincere thanks to Professor Rahman and Professor Singh for giving excellent coverage to the whole ambit of smart grid in such a cogent manner that the extreme complex issue of designing and maintaining smart distribution grids appears to be a simple one to even a layman like me. We are extremely grateful to both of you, sir, for kindly sparing your valuable time to be with us and educate us on this subject. We offer our sincere thanks to our esteemed moderator, Professor N. Kumaresan, who has nicely conducted and steered the webinar. And there is one renowned personality who is behind the planning of this entire webinar, and he is no other than Dr. Ramakrishna Kappagantu, our friend, philosopher, and guide. So we are really thankful to you, though you are not present as a panelist, but we are really thankful to Professor Kappagantu. I also offer thanks to our source of inspiration, Mr. P. Rajamani, our chairman of the Electrical Engineering Division Board, for kindly gracing this occasion and interacting with the participants. Last but not the least, I thank my colleague, Mr. Sudhir Chakraborty and others in IEI headquarters, and Mr. Devraj Thakur of NSDF IEI for arranging the webinar with precision. With this, I seek permission of everybody to end the webinar. Thank you. Stay safe and healthy. Good night or good evening right now.
Thank
you,
you.
sir.
Dhanyavad, Dr. Shankar.
The timing.
Thank you.
Professor
Thank you.
Rahman.
Thank you. Take care. Bye.
Okay, sir.
Thank you.
Thank
sir.
you.
Bye-bye.
Bye, sir.
Bye-bye. Take care. Bye-bye.
So with the permission of the chair.